Welcome everyone to our project presentation for Big Data Analytics CS63. The topic for our project is Visual Art Generation using TensorFlow. Let me introduce the team members. Myself, Amay Umbradia, one of the team member along with two other colleagues, Gurjit Singh and Deepika Sinha have contributed to the project.
Hello, I'm Gurjeet. I and Amey will talk about the interesting project presentation.
The content slide here shows that is shown here on slide 2 consists of problem statement. What exactly is the use case for visual art generation? What were the different techniques we were used to demonstrate our project? We also used different types of optimizers for comparing its performance in terms of time and loss accuracy, which is a trade-off while choosing an optimal one. Lastly, we want to demonstrate here our several attempts and challenges faced with the big data tools in terms of time and money while implementing multi-style visual art generation.
Next, we will show various technology used, for example, Amazon Web Services AWS with GPU instance for high computation. Along that, we use TensorFlow, which is Google's next latest tool. We use deep learning with convolutional neural network. More details in the following slides. The usage of dataset and models was quite interesting. While training our input images, we used 82,000 images while use VGG16 and VGG19 of 16 and 19 layer model for performing style loss, content loss for visual art generation. Lastly, we will show you the demo of for all the techniques and the experiences, challenges, knowledge gained during the whole process.
The main objective of our project is to show how a painter or artist can apply their imaginative styles to any input image and generate new image.
It is interesting to see how deep convolutional neural network work play a role in this generation, along with usage of amazing high computational and power GPUs.
The main idea in this project is highlighted in this slide. Basically, we have an input of content image and style image, which is passed through a model of VGG16 or 19, where convolutional and activation functions interact to produce a new artistic image.
The VGG model here is pre-trained on 82,000 images, and the contour of the content image while texture of the style image is mixed together to generate the new image.
Our project is broadly divided into three sections. Section 1 is the main highlight of our project because this is where we are using two different techniques to generate new image, which involves the usage of deep convolution layers, where the contour of the content image and the texture of the style image is used for the new image. The style transfer technique copies the color distribution of the style image, which might be undesirable in many cases. So there is an option to transfer the style without transferring the colors and preserving the content colors.
The style transfer or color transfer technique with a simple gradient descent optimizer might not output the preferable result in terms of style loss or content loss. While it might also take more time depending on the resolution of the image and the complex texture of the style. Therefore, in section 2, we have demonstrated the usage of the different algorithms like gradient descent optimizer, AdaGrad optimizer, AdaDelta optimizer, Adam optimizer, RMS prop optimizer, and LBFGS optimizer, which is basically our perform adaptive approach of learning rate or step size in order to trade off between the time and the loss accuracy. In the last section describe the multiple attempts and experiment on usage of the big data tools in terms of money and time for implementing the style transfer technique by combining more than two styles to the input image.
This slide illustrates various big data tools and platforms we used during our project. We used TensorFlow, which is an open source software library for machine learning, along with Keras, which is a deep neural network API. Of course, the other is the deep convolution neural networks computing it on Amazon Web Service instances of 8 GPUs, which is called P2.8x large. On a side note, it costs $7.2 per hour and takes 48 hours to request this instance.
For AWS, we use Audacity Community Image, which is an excellent image as they have installed relevant libraries necessary for the project. If the GPU is not used, then our project execution can range for 3 to 4 months on CPU. The type of GPU we used was NVIDIA's Tesla K80, which is used for fast computation. An alternative and the interesting platform to create AWS instance was Floyd Hub, which also has high performance GPU. Also, with all these tools, we have Python 3.5 from Anaconda, FileZilla for FTP to AWS, and Cygwin to SSH to AWS, and various other commands. For training our model, we use pre-trained model VGG16 for style transfer and VGG19 for optimizer comparison. The image on the right shows the directory has to be listed while implementing the basic style transfer with color preservation technique.
This model has a very high test accuracy of 92.7% while classifying 14 million images into 1,000 classes, which is an impressive accuracy rate. It was developed by Simoyan and Zisserman from University of Oxford. The link has been provided to download the model with its weight and bias. The VGG web model website has the code in the TensorFlow, which is called VGG16.py. It includes a pre-processing layer that takes the RGB image with the pixel values in the range of 0 to 255 and subtracts the mean images calculated over the entire ImageNet training set.
The style loss is calculated from all the layers of the convolution neural network, and content loss is extracted from the fourth layer, which is output to the gradient descent, thus generating new artistic image.
The loss function for the content image tries to minimize the difference between the features that are activated for content image and for the mixed image at one or more layers in the network. This causes the contours of the mixed image to resemble those of the content image. The loss function for the style image is to minimize the difference between the so-called gram matrices for the style image and the mixed image. This is done at one or more layers in the network. We use TensorFlow to automatically derive the gradient for these loss functions. The gradient is then used to update the mixed image. This procedure is repeated a number of times until we are satisfied with the resulting image.
On color transfer technique, we use linear method, which is very effective for colored style transfer. It can be seen how the color for the content image, which is blue, is still preserved in the output image while the style is still preserved. This style slide shows the comparison of using the algorithm with and without color preservation technique.
Here are the list of optimizers starting from simple gradient descent to add a grid, add a delta, adaptive moment optimizer, RMS prop, and LBFGS. All these optimizers adapt the learning rate in different ways. For example, it might aggressively reduce the monotonic decreasing learning rate or increase it with the larger updates for smaller updates on frequent parameters.
Here are the output of all the optimizers if the artist had to choose which one looks visually good. Then it would be one with the LBFGS, which it shows sharp contours of content image and the proper texture of the style image. This slide shows the feed-forward convolutional neural network, which include different convolution layer pooling that we use for styles transfer. There are several graphs of different optimizer, and we show one of them.
In terms of visualization, apart from the TensorBoard graphs for the previous convolution network, we also have the graph between the time and the loss accuracy. It can be seen here that the LBFGS and the RMS prop performs the best in terms of loss, and it rates over 400 times in less than or around 300 seconds.
This slide shows the style loss, content loss, total variation loss for all the optimizers using the TensorBoard graph. This slide shows the histogram for all the optimizers. Now let's talk about the multi-style visual art generation. In the multi-style visual art generation, we took two style images and we combined to get an output image, and we had to use the content image for getting the output. Here we use here we use the approaches by using the instance normalization instead of the batch normalization that was used previously. The following slide here is to show the implementation experience challenges of the big data tool we went through.
There were several attempts to executing the multi-style visual art generation. Traditionally, when we started, the first attempt was to download the 82,000 images and then train our model on our input image, which had a very good resolution. What it came out that we need to have at least 10 epochs with approximately 5,000 iterations in order to have a well-trained model, and then combining the multiple styles to the input image. So as we started running, we saw that it took approximately 2.5 hours just to complete 2,000 iterations of one epoch. And thus we estimated that with 10 epochs, it might take 50 plus hours to just do the entire process of training. At this time, we were short of AWS credits and we wanted to show some alternate ways. So that's why we went to attempt 2.
In the attempt to, we reduced the training images to 40,000 and we also reduced the resolution of the image. But we still ended up with more than 24 hours for training. So we did attempt 3 with reducing the images to further 10,000 to 11,000 images. But as expected, by the training on the lesser number of the images, the output was not properly modeled and we got a blur style image trained on the input image.
So the last attempt we tried to make is to find an alternate platform, just because we used up all the Harvard AWS credit, which were free, and approximately $200 from our pocket on AWS instances. So we thought that let's try to find an alternative platform, and we found Floyd Hub, which also had a GPU, high power GPU instances. The other good thing about Floyd Hub is that it already had a pre-trained model, but unfortunately we could not find a trained model for our style images. So just we had like few hours left on the GPU instances for Floyd Hub. We tried to train only 100 images and try to combine 2 style images with 50% weight contribution of each. And apparently, since we had since we had trained only on 100 images, the output didn't look so good. Or whether if we had trained on more images, or approximately 50,000, then the output would have looked much better. So these were all the attempts that we used and the experiences and the challenges we faced with the big data tools on implementing multi-style visual art generation.
So what is the knowledge we gained in this project? We learned a good amount of knowledge here and we invested good amount of time and we learned about the big data tools, techniques, alternative platforms, and the workarounds in that. We also learned about how to use the TensorBoard with the Keras API, simplifying the deep neural network. And we also had good, interesting knowledge about the AWS instances, like changing the paid instance to the free instance so that to reduce the cost, snapshotting the volume of the instance when not in use to reduce the cost. And then we had a key value pair to safely connect to the AWS by generating the PEM file. We also understood about the very deep convolution neural networks such as VGG16, 16 layers, VGG19 of 19 layers, and how a style and the content loss after imputing the gradient descent and feeding it back and output our style transferred to artistic image. We use FileZilla here to transfer the data back and forth from the local machine to the AWS. So here we learned about that. And then we also learned about different optimizers by comparing them, and we compared their performances. And we found there can be a good trade-off between the time and the loss accuracy. And we also found when we are doing the multi-style, we found that there can be a free instance from the Floyd Hub that can be used here, and that can save a good amount of time. But there was a still good amount of time investment.
Okay, let's go over the pros and cons on the entire project. Definitely a main advantage is that the artist can now transform their imagination into different types of styles and implement on any image using our style transfer technique. Also, depending on the preference and how visually the image looks, The artist is now not limited just to is not limited using just the ordinary style transfer algorithm, but they can actually use color transfer technique that can preserve the colors on the content image. Also, we did not limit the artist to just implement one style, but with multi-style algorithm, we can combine multiple images to the input image. And the VGG16 and the 19 pre-trained models were very helpful since they were already pre-trained. And this process of developing the artistic image became much quicker. The disadvantages on the entire project that we saw was since the VGG16 and 19 are deep layers, approximately 16 to 19 convolution layers, it required huge computation machines such as AWS P2 8x large, and it cost us very high. Since utilizing this GPU is expensive and the instance price was $7.2 per hour, we spent all the free credits of the Harvard AWS credits and approximately $200 from our pocket. The current imputation takes 50 plus hours with GPU, but if a CPU is used, then it may take 3 to 4 months.
So we also faced challenges while working on this project. We had to learn about the AWS, Amazon AWS instances, like EC2 instance, like what instance to use. So we use like P2 8x large. And then we had to learn about the different libraries that was not installed. So we had to install some of the libraries. But in this way, we also found Audacity community AMI that has pre-installed libraries, so we use that. And the main challenge were faced was mainly during in the executing the multi-style transfer, which combined more than one style to an input image. And we had invested attempt 1, attempt 2, and attempt 3 by changing the number of images, iterations to go to that and find the final output. So approximately going through that, we invested $200 plus free Amazon AWS credits and with a huge amount of time on this project and to successfully complete it for the multi-style algorithm. These are the references which we use for the VGG style transfer, gram metric, color transfer, multi-style, and Floyd Hub. Thank you everyone for listening to our presentation. Thank you.
Thank you.